Welcome all. Today we are going to understand about least square regression. What is regression analysis? This is a method, statistical method, to find the relationship between a dependent variable and one or more independent variables. And generally, we do this regression or statistical method with a model to find what is the relationship and extract the coefficients from that relationship so that we can understand about the data in a better way, and also we can predict the values. There are different kinds of regressions available. Most commonly used are linear regression. If we have only one independent and one dependent variable, and if we have more independent variables and one dependent variable, and they are almost varying linearly, then we go for a multiple linear regression. If the way the independent dependent variable is varying with given values of dependent variable x is not following simple linear kind of phenomena, then people will go for a polynomial regression, and there are other regression models are there depending on uh, looking at the data and finding assuming a most probable uh, relation between the dependent and independent variables, one can go with the kind of regression models that they want to fit so that they can get some better analysis as well as a better prediction. Well, in this case, we are looking for simple linear regression, or we can say as a straight line fit, linear fit or straight line fit. That is the first one that generally people most of the times will look when in physics. If you take the example of finding the band gap based on the variation of current with the temperature or conductivity with the temperature, you can say this model we can use our simple pendulum experiment, the finding from the variation of time period square with the length of the pendulum, and from that obtaining the value of g. Some you can take these kind of examples where the independent variable like conductivity and independent variable temperature and dependent variable conductivity. If you take a straight line, they follow a linear way behavior. And if you say time square, that is a dependent variable and independent variable length of the pendulum, if you look at that also follows a linear behavior between them. They are directly proportional. In such a case, we can go for simple linear regression. So the model that we can take is y equals to b naught plus b1 x plus epsilon, where b naught is the y-intercept, b1 is the slope of the line, the linear fit we are doing, and epsilon is the error. And from this graph, you can see uh, uh, the difference between the value on the line and the observation point. This difference is called the error. And where the straight line is now intercepting the y-axis is called the y-intercept, and the slope of this line with respect to the independent variable, that is beta 1. Okay, so when you fit the data, what happens is this slope will change continuously until the sum of these error squares are minimum. We will look at that. So for the getting the for fitting a straight line for the observed data, what we are going to use or any mathematical model, statistical model to fit for the observed data, what we are going to use is called least squares method. The objective of this least square method is to find a best fitting a curve or line that minimizes the sum of the squared residuals or errors. What is residual or error here? The difference in the observed value and the predicted value. Like you see, the difference in the observed value is this one. What we have, the orange point, and the predicted value is the point on the fit that we are taking for a given value of independent variable. Let us say here x. What is the predicted value y on the green line, and what is the actual value that we have? That is a orange point. So the difference in these is you can say as error or residual, and what the model when we fit what it will look for is for what slope this sum of the squares of these residuals is minimum. So when we are doing the regression or fitting, the model will do minimization of sum of these residual squares yi, that is observed value, minus y cap I, that is predicted by the curve square. That okay. Then the slope from this regression can be found by the formula beta 1 equals to sum of x1 minus xi minus x mean value. That is xi is the predicted value and x bar is the mean value into yi minus y bar. Yi is what we have predicting, and y dash is the mean value divided by x minus xi square, sum of. Okay. Likewise, intercept will get beta naught equals to mean y values minus beta 1 of x mean values. From this one, we'll get intercept. These are all from what where we are fitting the curve. These values are from the points on the curve that we are going to get after minimizing the sum of residual squares. So here, whether our whatever the fit that we got, a linear fit or any kind of curve fit, is it how far it is good? Can based on the fit, can we whatever the predictions that we make for different values of independent variables, is it good or what? Is it reliable? How far it is reliable? To know that, what we need to find a coefficient called as r square, coefficient of determination. What it will do, it measures the proportion of variance in the dependent variable explained by independent variables. Generally, it ranges from 0 to 1. If r square is 1, it is 100% very good model. But whatever the prediction you do is 100% accurate. If r square is 0, then our model is not good at all. So what we have to do is we have to find a statistical model that gives you better r square, which is almost equal to 1. Okay. So how it is found is r square equals to 1 minus SSR by SST. What is SSR? Sum of the squared residuals. Like the residual equals to the difference in the predicted y value and observed y value. And you take the squares of that and you add them. That is called SSR. SST measures the total variance in the dependent variables. Sum of the total sum of the squares of the dependent variables. Okay. So for each y value on the regression, residuals are calculated, the SSR and SST are calculated, and from there we get the R square. So let's do some practice with some random data. What we are doing to take is this data. You can see here we have x is the independent variable. It is 1 to 20. And if you look at y, the relation between x and y, you can see that 1 equals for 1, y equals 2.1. For y, x is equal to, we have x, y is equal to 3.8. For x equals to 3, y equals to 6.2, like that. So if you look at these y values, we find it is approximately y equals to 2x. Find that y is approximately equals to 2x. Okay. So let us see how far what we are going to do is we are able to get whether that slope as 2 and how much error we have and what is the r square, how far our model will be good. For this, we are going to use a Python packages. And in this one, the first important module that we are going to use is NumPy. Provides us to read the text, to write some mathematical values, etc. Arrays, create arrays, and other things. Matplotlib.pyplot to plot the data. And we are going to fit the data using curve fit function from which is being imported from scipy.optimize. And we saved the data in a text file. Okay, look here. It's a very simple text file what we have. And this name is given as fit.txt. Okay. The first thing what we need to do is we need to read this data file. We have to load the data file and we have to read this data file. So for that, what we are going to do is we are going to use from the NumPy module load txt file, load txt function, which loads the txt file, and we need to inform what kind of data it has. Generally, by default, it will choose float, and if you have strings or integers, we can say. So this is what we are going to do. File dot data file underscore data equals to np. That means we are importing numpy as np. So np dot load txt. What is the file name? Fit data dot txt. And the data type is float. Okay. So to know whether we are importing it correct data or not, we can say simply print file data, and you can see they are same. So we have imported the correct file without any changes. Just we are reading the file. Now, what is that? This has one in and one variable. How to read these columns now? So in Python, the indexing starts with 0. So the first one we can assign to x data as 0 column, and the first column is actually this is one column. You can assign as y data. How we do that? X data equals to from the file data that what we have imported, we want to import the first column, so 0. And the second column, y data, since in Python the indexing starts with 0. Now instead of 2, we have to write 1. Y data equals to file data, that is the file we have. Column minus comma 1 means, column comma 1 means we are importing the first column. If you write here 1, then it is importing the row. Okay. Then let us see, let us plot it and let us see what kind of relation they have. So we can use the PLT function from here to plot the these two data point, x data and y data. So PLT dot plot x data, y data, scatter. O means here we are putting scatter. Then you can see this is x data and this is y data. And if you look at, they are just almost varying like linearly. So what we do now, we can write a small function y equals to ax mx plus c. So fit function we can write, say whatever we want, because we are fitting a function. So fit function, x is the independent variable, a and b are the coefficients, and we want to predict the values y equals to ax plus b. Like, because it is almost like a straight line, we are using mx plus c. Okay, then return y. And when we what we are doing is, now we are using the curve fit the module SciPy, function of SciPy, and then trying to fit this function with what the data we have, x data and y data. Okay. So, and we want to obtain the parameters as well as the covariance. So we are writing parameters at comma covariance equals to curve fit. What we have to fit? We have to fit the function, whatever we have defined here, with respect to the x data and y data, that what we have. Okay. Then what we want to get? We want to get the slope and the y-intercept. So we want the parameter slope as parameter 0, and intercept as parameter 1. Okay. Then what we can do is, we can get the predicted values of y by using the fit function data already what we have fitted, and the parameters that what we are obtaining after fitting the function with respect to the x data and y data. So this is fit y is nothing but the prediction of y with respect to the curve fit model, that what we have used here, linear model, using the x data and the parameter slope and intercept, and let's see how far they are good. Okay. So we are calling the parameters as slope and intercept only. So let us run now this one by one. So just we are importing the data, modules and data, and then what is we are assigning the first column to x and the second column to y, and just let us plot this data. We have this one, the almost linear variance. Then we have defined the fit function as y equals to ax plus b, and we are using the curve fit function of optimize to fit the function with respect to x data and y data and obtain parameters and covariance. And now what are the parameters we have? We are having slope and intercept. That's what we want, a and b. So you can see now slope is 2.017. It's almost 2. That's what we are saying. No, y equals to mx plus c. And when you look at the data, it is approximately y equals to 2x. Approximately. So how in the model we are getting now good value as of the slope as 2.07, and intercept is minus 0.08. That is almost it's going passing through the almost origin. Then what we do now, we predict the y values using these parameters, slope and intercept, and let's see how the predicted values and observed values match with one another or not. So the orange line is the predicted curve, and the blue scattered points are our actual observed data. And you can see that this orange line, that is fitted curve, is all very good, having very good match with the observed scatter points, observed points. So that means our model is very, very good. And now you can see the error for A is 0.00928. So it's a very good fit. Error is very, very small for what we have, the slope. So in this way, we can do the curve fitting. And if it is a polynomial function, yeah, you can simply define the polynomial function here, and then fit the you can use the same process and fit the data and obtain the parameters. Okay, this is all from my side. Thank you.